In Unit 3, we're going to talk about what makes a function linear. And in Lesson 1, that's exactly what we're going to analyze. So the first one has the tables below show the values of 4 different functions for a given value of x. And it wants to know which tables represent a linear function, and then we're going to explain why. So if you look at all the tables, we go 1, 2, 3, 4 in the x column, 1, 2, 3, 4. So really what we can just worry about is our f of x, our g of x, our h of x, k of x, which in other words are our y columns. And the key to being linear is your average rate of change is equal throughout. So as we check each interval, we have to be adding or subtracting the same number the whole time. So if I look at my first table, 1, 2, 3, 4 on the x's, so then f of x is 12 to 19, so plus 7. 19 to 26 is plus 7. 26 to 33 is plus 7. So the answer, or f of x, is going to be a linear function. If we look at g of x, we are plus 2, we are plus 4, and then we are plus 8. Well, that's not the same every time, so not a linear function. H of x, we're plus 3, we're plus 5, and plus 7. Again, not the same rate of change every time. And then last but not least, we are plus 6, we are plus 10, and plus 14. So that's not the same every time. So the only one that is going to be a linear function is going to be table 1. And again, if we were going to explain what that is, or why that is, I should say, the average rate of change is the same everywhere. And that key piece is everywhere. It's got to be in all facets of the table, all facets of the equation. Every time you do the average rate of change for something, it has to be the same if it's going to be a linear function. In our second one, which statement could be modeled using a linear function? Again, we're going to look for that add or subtract the same thing every time. Each time you bounce a ball, it bounces 1/2 the height of its previous bounce. Well, 1/2 is really a multiplying problem. Those are next unit, not this unit. The cost of frozen yogurt is $2, and each additional topping costs 50 cents. So each additional topping costing 50 cents means we're going to be $2 plus 50 cents each time. So that could be a linear function. We'll hold on to that one. Sales tax for a clothing purchase is applied at a rate of 8.125%. Our percents are almost always multiplying. So that one's out. And then last but not least is our table. Well, we are plus 3, then we are plus 5, plus 7, and plus 9. That's not the same. So the only one that we have as a linear function is going to be choice 2. And again, that's because the frozen yogurt is $2, and then you add 50 cents for every topping that you buy. The table below shows the balance in a bank account after a given number of years. Calculate the average rate of change in the account from 0 to 20 and from 30 to 50. So once I see average rate of change, our y2 minus y1 over x2 minus x1 formula should be popping into my head. So for 0 and 20, we are 0, 380, and we are 20 and 832.63. So we have x1, y1, x2, y2. So be very careful here. Make sure you use your calculator. Don't want to try to guess at what's happening to these numbers. So when I do that in my calculator, 832.63 minus 380, I get 452.63 over 20 minus 0 is 20. When I divide that by 20, I get an average rate of change of 22.6315. So now I'm going to do the same formula here, but now I'm going to do it from 30 to 50. So 30 is 1232.49, and 50 is 2,754. So same deal, I've got x1, y1, x2, y2. So 2,754 minus 1232.49 over 50 minus 30. So when I quickly plug that into my calculator, I get 1,468.05 over 20. And when I do that division, I get 73.4025. So I get two very different average rates of change. So does this situation represent a linear function? And the answer is no. The average rate of change is not the same everywhere. All right, so again, if it's going to be linear, that means our average rate of change needs to be the same throughout the entire table.